Hi, I'm Colin. In this module, we're going to revise the notion of a logarithm before analytically comparing the following two logarithms to determine which one is the larger number. Let's start with the basic definitions. Suppose we have y as a function of x, given by y is equal to some constant a to the power of x. Then a is called the base, and x is called the power. These sorts of functions are called exponential functions. And is characterized by the fact that the independent variable, here that's the x, is in the power. This is in contrast to polynomial functions, for instance y equals x squared, where the variable is in the base. Now, a power is sometimes also called an index. Sometimes it's also called an exponent. And sometimes it's called a logarithm. Specifically, if y equals the base a to the power of x, then we say that the power x is equal to the logarithm of y to the base a. Thus, there is nothing really mystical about logarithms. They're really just powers. Specifically, the logarithm of a number is the power to which the base must be raised to produce that number. Here are a few quick examples. The log of 8 to the base 2 is equal to 3, because 2 to the power of 3 is precisely what gives you 8. And here's another example. The log of 1000 to the base 10 also turns out to be 3, because 10 cubed is what gets you 1000. Always be sure to specify the base when you're working with logarithms. Without a base, the logarithm itself is meaningless. Now, on your calculators, you'll notice a button somewhere that says log. This button specifically calculates logarithms to the base 10. You should take out your calculator right now and verify that if you press the log button and type in 1000 and then press the equals key, you'll get 3. Since, as we worked out earlier, 10 to the power of 3 gives you 1000. There is another button next to the log button that says ln. This button calculates logs to a very special base, log to the base e. Now in mathematics, the pronumeral e is called Euler's constant. Which is an irrational number that's roughly equal to 2.71. Another irrational number you should be familiar with is the number pi. Anyway, Euler is one of the most accomplished and famous mathematicians of all time. So what's so special about this number e that's named after him? It turns out that the particular exponential function that we get by choosing our base to be the constant e has the very special and unique property that the function outputs its own slope at every x value. That is, for every x value you throw into the function y equals e to the x, sure, you get its y value. But this y value also turns out to be precisely the slope of the function at that point too. The idea of slopes for general functions will soon be formalized when you begin your studies of the differential calculus, which is one of the core components of this unit. Now, log to the base e is commonly referred to as the natural logarithm. And is one of the most important logarithms in mathematics. That's why it's given its own special designation, ln. Finally, I want to establish a very special relationship between exponentials and logs. Notice that for any input x I throw into the exponential function, I get the output y. But then when I take the log of this y value to the same base a, I actually recover the original input x. This shows the very important fact that y equals a to the x and y equals the log of x to the same base a are actually mutually inverse functions and thus undo each other. In other words, the operations of exponentiating and logging are inverse operations of each other, similar to how adding and subtracting, or multiplying and dividing, or cubing and cube rooting are mutually inverse operations. Thus, provided that the bases are the same, the operations of exponentiating and logging cancel each other out, and you'll be using this concept extensively to solve equations that involve logs and exponentials. Let's now answer the following question. Which logarithm is bigger? Log of 17 to the base 4 or log of 24 to the base 5? Importantly, to train our understanding of logarithms, we want to deduce the answer to this problem analytically without the use of a calculator. Okay, to begin, let's try to understand the problem a little better. These two logs are ultimately just numbers. So if we could work out exactly what these numbers were, we would be able to compare them easily and see which one was larger. So for log of 17 to the base 4, we're trying to find the power to which 4 must be raised by to get 17. In other words, 4 to the power of what gives me 17? Well, that's not easy to answer. But I do know that 4 squared gives me 16. Therefore I know that log of 16 to the base 4 is equal to 2. Now, if 4 squared gives me 16, then to get 17, I would have to raise 4 by a power that's a little bit bigger than 2. So log of 17 to the base 4 must therefore be a little bigger than log of 16 to the base 4. Okay, let's now look at log of 24 to the base 5. Here, we're trying to find the power to which 5 must be raised to get 24. In other words, 5 to the power of what gives me 24? That's not easy to answer either. But I do know that 5 squared gives me 25. Therefore I know that log of 25 to the base 5 is also equal to 2. Now, if 5 squared gives me 25, then to get 24, which is something smaller, I would have to raise 5 by a power that's a little bit smaller than 2. Therefore, log of 24 to the base 5 must be a little bit smaller than log of 25 to the base 5. Thus, we've shown that log of 17 to the base 4 is a little bit bigger than 2. And log of 24 to the base 5 is a little bit smaller than 2. Which ultimately means that log of 17 to the base 4 is bigger than log of 24 to the base 5. Okay, so we know that one of the logs is a little bit bigger than 2, and the other is a little bit smaller than 2. If you did want to work out precisely what the numbers were, you wouldn't be able to do it directly from your calculator, since your calculator only has buttons for logs to the base 10 and base e. Here, you're looking at logs to the base 4 and 5, which doesn't directly have associated keys on the calculator. Well, thankfully there is a formula that converts the log of an unfriendly base to one that would be nice to work with, such as log to the base e. The formula says that if you have log of x to the base a, where a can represent an unfriendly base that isn't easy to work with, then you can write this as the natural log of x divided by the natural log of a. Thus, we have written a log to the base a as the quotient of two natural logarithms, whose values you could then work out using your calculator. By using the change of base formula, log of 17 to the base 4 can be converted to ln of 17 divided by ln of 4, which, when using your calculator, gives approximately 2.04. Therefore, 4 to the power of roughly 2.04 gives you 17. And similarly, log of 24 to the base 5 can be converted to ln of 24 divided by ln of 5, which, when using your calculator again, gives roughly 1.97. Therefore, 5 to the power of roughly 1.97 gives you 24. Alright, I hope you found that useful. See you next time.